Hey guys, Mr. Betts here. Let's take a look at an example where we are finding the area of a region bounded by multiple curves. In this example, it's a little bit tricky because we can see that for part of the region, if we draw a Riemann sum rectangle, it's bounded above and below by the functions in the problem. But on another interval, it's bounded above by the line, but below by the x-axis. So this is an example of one where we're going to have to split it into separate integrals. And we can see that at this point, the bottom function changes from that parabola to the x-axis. So we are going to have to represent this area with two separate integrals. One of the integrals for the left part of the region here is going to be going from that intersection to where the parabola intersects the x-axis, or the zero for that parabola. And then the other area is going to go from that point over to where the line intersects the x-axis. So we have to find a few things, and we're going to use our calculator to do this. One intersection, it looks like it's at x equals 2, but we do want to confirm this with our calculator. So I'm going to plug into my calculator y1 is this function, and y2 is this function. And then I'm going to check the intersection of those two, and we can actually confirm that that intersection is at x equals 2. We want to make sure that we get that right, because if it's like 2.0 something, we're going to get a bad answer if we just use 2. I'm also going to find the intersection of y1 with the x-axis, so I'm going to use the 0 function on my calculator, and I want to make sure that I'm using y1, so find the 0 of y1, and that's going to give us a value that is about 3.1623 and so on. And since I'm going to be using that to get an answer later, this is an intermediate answer. So I'm going to take that and I'm going to store it in my calculator for the variable a. So we want to find that intersection, go to our home screen, store it for the variable a, and then I'm going to use that as part of my integral expression later on. The last thing that we want to do here on our graph, for our limits at least, is to find the 0 for that line. This is one that we can find pretty quickly using algebra. We can confirm that that function is going to be 0 when x is equal to 8. So it does look like 8 on the graph here, but we can confirm that intersection is at x equals 8. So that's going to give us the limit for our other integral. So I'm going to go ahead and set up my integrals here. So the area of the whole thing is going to be the integral from x equals 2 to x equals a. And I'm just going to use a here because I did include in my work that a is equal to that 3.162 and so on. And on that interval, if we imagine a Riemann sum rectangle, the upper function is going to be, and I'm just going to use the names of the functions here. So the upper function is that line, which is g of x. We could also put in here just the negative 8 or negative x plus 8 if we wanted to, minus the lower function, which is f of x. And don't forget that differential with our integral. And I forgot a parentheses in there. The rest of the area is going to be given by the integral from a to 8. And on that interval, if we imagine a Riemann sum rectangle, it's bounded above by the line, which is g of x, and below by the x-axis. So since it's bounded below by the x-axis, we don't need to include the bottom. We could think of this as g of x minus 0 if we wanted to, but we certainly don't need to do that. And then that's going to be with respect to x. So we can use our calculator to evaluate these separately. I would recommend, if you do evaluate them separately, make sure that you either store those values in your calculator so that we get the full accuracy from our calculator, or you can type it into your home screen as one big expression. So if you're typing this into your calculator on your home screen, remember g of x we've plugged in for y2, f of x we plugged in for y1, so we can just type it into our calculator using y2 and y1 in those places. Also remember we stored a in our calculator, so we can use just that variable a as the upper limit. If you do evaluate these separately, we get values for these integrals that are going to be about 2.5497 and so on. And then for the second one, we get 11.7017 and so on. And then adding those together, we're going to get a total area rounded to 3 decimal places of 14.251. So there are a few places here that we're using our calculator to get intermediate answers. And this is a good example to practice using our calculator and storing values so that we don't lose any accuracy in our answers.